let's talk about syntactic islands. Syntactic islands involve what are known as WH dependencies. And so let's look again at that example I was talking about before a little while ago. This kitty was bought as a present for someone, and Lily thinks this kitty is pretty. And so we might want to ask, who does Lily think the kitty for is pretty? And we can't. Instead, we kind of have to ask it a different way if we want to get at that content. What does Lily think is pretty, and who does she think it's for, right? But the question is like, why can't we ask it this way? Who does Lily think the kitty for is pretty? Like, we're making a frowny face, it feels terrible. What's going on, right? What's the problem? And one answer is that there is a dependency between the WH word who and where it's understood as the object of for. The kitty is for who, and that's the link between the WH word and the gap. And this dependency is strongly dispreferred in English. Like, we really, really, really don't like it. Why not? One explanation is this dependency crosses a piece of hidden structure in our minds called a syntactic island. And the metaphor is that if you're on an island, there is no crossing into and out of the island. You are surrounded by water, you shall not cross, right? And so therefore, if you have a dependency that tries to cross this hidden island structure, wherever it is, it's very bad and we do not like it. So, okay, this is one type of island. It's been called a subject island. Here's some other ones. So we have Captain Jack Sparrow. He's somewhat tricksy, and he claimed he bought something. We might want to ask about it. What did Jack make the claim that he bought? And that also, to most English speakers, feels kind of bad. That's been known as a complex noun phrase or complex NP island. If we go back to Tricksy Jack, he claimed he bought something. Elizabeth wondered if he actually did, and if so, what it was. And we might want to ask about this situation. What did Elizabeth wonder whether Jack bought? Again, not so great. That's been called a weather island. We go back to Tricksy Jack. He claimed he bought something. Elizabeth worried it was something dangerous, because knowing Jack, you need to check these things. What did Elizabeth worry if Jack bought? Again, not so great. This has been called an adjunct island. And the important thing is it's not just about the length of the dependencies, because you might notice there's kind of a lot of words here in between. Maybe it's just you don't like long dependencies. Not necessarily, right? So we can say, what did Elizabeth think? We can make it longer. What did Elizabeth think that Jack said? And that's actually almost as long as most of these guys, and that's still pretty good. We can make it even longer, really. What did Elizabeth think Jack said Lily saw? And you might kind of start to forget who's doing what, but it doesn't feel bad in the same way that who does Lily think the kitty for is pretty feels bad, right? So there's some kind of difference going on. And in fact, English adults judge these island crossing dependencies to be far less acceptable than many others, including other dependencies that are pretty darn similar, except that they don't cross syntactic islands. So that's some adult information. And then we have actually behavior from kids. English learning children strongly disprefer at least one of these, the complex noun phrase, complex MP island. What did Jack make the claim that he bought? They really don't like this compared to, again, other dependencies that they have preferences about. When we go back to adults, it turns out that the frequency of a lexical item like the verb, say, or whine, can also affect adult acceptability judgments of potential syntactic islands. In particular, adults are usually pretty happy with what Elizabeth say that Jack saw, but it starts to feel kind of more islandy if you say, what did Elizabeth whine that Jack saw? It starts to feel not so good, and that's really just changing what verb you're using, right? So again, this is a whole variety of different types of behavior that we're observing in adults and children about this WH dependency knowledge. And these judgments and preferences or dispreferences are basically a measurable thing. They're a type of observable behavior we can measure and that can signal the successful acquisition of syntactic island knowledge, right? Like if you can generate these behaviors, these target behaviors, then you've internalized something that seems right about WH dependencies. And so, again, there are different patterns of behavior. This is a more formal representation on different figures and graphs, but the point is, these are things we can look at, that we can try to explain, behavior that we can try to generate, right, to signal that, you've internalized the right knowledge about WH dependencies. You're able to generate the observable behavior that signals knowledge of syntactic islands. So that's the target, right? These judgments and dispreferences are serving as our target. They're an outcome we can measure and measure against. Okay, so this is the target of acquisition, but here's the question. How could a child actually learn this? Good question. Well, let's use a computational cognitive model to help figure this out. Now, okay, again, a computational cognitive model is meant to encode a learning theory. So what's a learning theory that our modeled learner could actually encode? Well, here's one. This one, and the idea is you're trying to learn the right building blocks of WH dependencies. So you're going to view WH dependencies in terms of the building blocks, whatever they are, and you're going to count those building blocks in the input. So what are we talking about? Let me be a little bit more concrete here. So the idea is that dependencies are represented as a sequence of what Perl and Sprouse in 2013 called container nodes. And the idea is if you're looking at, this is just one example syntactic representation of what did you see. But the idea is that if you look at this gap, see what, right? You're looking for the phrases that contain the gap, but not the WH words. So if you're looking at what those are, you're like, okay, the gap's here. Looks like if I go up here, a verb phrase and then an IP inflectional phrase, and then we get up here, oh, there's my WH word. So our path, as it were, our syntactic path is something like start IP VPN, and that kind of characterizes or describes this WH dependency. And you can do this for any WH dependency you like. So what happens is a really short one with just an IP as a container node path. What did she want to do? You get a little bit longer, right? IPVP, right? But you just follow the path, and that connects your WH word to your gap. And so the idea is that dependencies that are much less acceptable have low probability segments along this path, low probability pieces. And so if children are breaking these dependencies into smaller building blocks, they can identify if a dependency has bad segments that is made up of one or more low probability building blocks. That's why it's important to think about breaking these things up into building blocks in the first place. So okay, now what about those building blocks? The theory then that we're going to try to implement is that the child tries to learn what the best building blocks are, quote unquote here. The guiding intuition is that the best building blocks are the most, quote unquote, efficient ones. All right, let's talk about efficiency. Efficient building blocks are going to allow the representation of current and future WH dependencies to be more probable. Why is that good? Why do we think that's efficient? Why? One idea is that higher probability things in general in your life are easier. So higher probability WH dependencies are going to be faster for you to process, whether you're comprehending them or producing them. If they're just higher probability, life is easier for you. So you're trying to find building blocks that make your input, your experience, your WH dependencies in your life more probable. How? Okay, so here's where we're going to use some reasoning. You're going to look for building blocks that are a balance between two things, how big they are and how fast they are to put together to make any WH dependency you might like. So let's look at this one. What did she say that he saw? It's kind of a longish one. And you might represent the structure like this, and if you kind of zoom in on the syntactic path, it maybe looks more something like this, right? Or you can think about it as being something like this, right? You've got this path that's connecting the WH word to where the gap is. Okay, so with that in mind, you can talk about the size of your pieces. Pieces can be small, so that many of them make up a WH dependency, right? And the thing about it is it may be slower to put together many small pieces because there are like a whole bunch of them and you got to put them together. But these pieces may get reused, right? And so that may make them faster to actually access to begin with. In fact, not just reused in the same dependency, but just like reused all over the place. So they're like faster to pull out to begin with, even though there are a lot of them. Now, the other option, the other extreme as it were, is that pieces can be big. In fact, so big that only one makes up a WH dependency, right? So one big chunk. And now the thing about this is that it may be faster to put together one big piece because you're not really putting anything together. You just take your chunk and you are done, right? But it may be slower. if this piece is used rarely. And in fact, the problem here is that you're going to kind of end up with one piece per WH dependency, so you don't use it that often. So like finding it in the first place, digging it out of your building block grab bag might just take you longer, right? So it seems like the most efficient option is probably a balance of both bigger and smaller blocks that collectively are faster to access and put together. And so, maybe this is just one example. You've got some bigger ones, you've got some smaller ones. There are many possibilities, many possible building blocks, and you're just trying to find the most efficient ones that make it faster on average to put together your WH dependency. So, great. How can children actually find the best balance? Good question. We're going to use some quantitative techniques, some math. We're going to use Bayesian inference to search through the hypothesis space of all possible building blocks and find an efficient set to explain the WH dependencies that children are encountering in their input. And so that's what our model child is going to try to do. So now we'll see if this model child can learn the target knowledge that real children actually seem to learn about syntactic islands. And we'll have the model child learn from the same kind of input that children encounter and for the same amount of time that we think they get to learn from it. So what does that look like? We can estimate, the input, like what is the set of WH dependencies, what kind of WH dependencies are they learning from, say from the child's tree bank of collected data of child language interactions. We can estimate like how long children get, turns out to be like 10.4 million minutes or so. You can sort of convert that to like how many dependencies do you actually like encounter during that time, which is maybe 2.15 million on average, say. Okay, so you get that many of this stuff. Can you get there? Can you get the target behavior? That is our question. And so what happens? Like, how did this model child do? Is trying to find the most efficient building blocks for those dependencies. And here's a reminder, here's what you're trying to reproduce. Again, I'm not going to go into the details of what these are, but these are just different patterns of behavior that we observe in adults and children, right, that signal internalized knowledge of syntactic islands. And so it turns out our model child can generate almost all of these. Like it's got this one, it can do this one, and it can mostly do this one. It kind of fudges a little bit on these data points, but it's not bad. It's just not perfect, right? So that's pretty good. And it turns out that that means the model child who encoded the efficient building blocks learning theory was actually able to generate almost all of children's target behavior, again with this little fudge point over here. So pretty good, actually. And it turns out this is also true even if our model child has childlike memory constraints that cause it to forget some of its input, right? Like, so it's like more childlike in the way that it's viewing and experiencing the data. And it still is pretty darn good. So it seems then that this learning theory of looking for efficient building blocks is implemented by our model child using math of counting things and reasoning using Bayesian inference is pretty good at capturing children's target behavior. So it may be a pretty good explanation, not perfect, but pretty good for how children acquire syntactic island knowledge from their input.